Okay, this video is an abbreviated version of the original, which had the objective of to learn how to identify whether an equation has one solution, no solution, or infinitely many. But it's going to have just the part about how you can create the equations for yourself. Creating equations that have no solution or infinitely many solutions is all about working from the answer backwards. Why would you be asked to do this? Well, the belief is if you can actually create the equation that does have no solution or infinitely many solutions, then you definitely have a good handle on whether on being able to identify equations that have no solution or infinitely many solutions. Okay, let's start with a situation where we have infinitely many solutions. So we're asked to create an equation that has infinitely many solutions. Well, every equation with infinitely many solutions results in two equal numbers. So let's start with two equal numbers. We got 12 equals 12. So I've got these two equal. That's the starting part of my equation. Now I can't leave it like that. I got to have some algebra in there. So we got to bring in the variables. Now the variables also need to cancel out. In order for those variables to cancel out, they have to be equal coefficients, and there has to be one on each side of the equal sign. So we're going to end up with something that looks like this, 3x plus 12 and 3x plus 12. 3x on this side, 3x on this side. Because when I subtract 3x from both sides, they'll cancel out. Well, this is basically the same expression set equal to itself, which is also a good way to tell when you've got an infinitely many solution equation, when this side of the equation is exactly the same as this side, even though they're a different order here, this 3x plus 12 and 12 plus 3x, it's still the same thing. When that happens, you have infinitely many solutions. Now, we can't leave it like that. That's just too simple. If that's the basic part there, we need to make it a little twist so it's not so obvious that they are equal equations there. So I'm going to try something like this. I'll take this one, which is the same expression. All I've done is take, on this side of the equation, I took the 3 out of the 12 and the 3, and I put it here. Did that reverse distributive property, and that left me with x plus 4. When I distribute these, 3 times x is 3x, 3 times 4 gives me the 12. This side's still the same, but now it doesn't look quite the same, and requires me to do a little bit of extra work to get there. Over here, I took the 12 and I split it into a 20 minus 8, and I put the 3x in the middle of those two numbers to throw off the game there. So this would still simplify to that 12 plus 3x. It's still the same exact equation. It's just now you have to do a little work to see that it's the same equation. I also went a little bit fancier over on this one here. Here I got really creative. The first part I didn't. I took the 3x and I split it into x and 2x, because those two add together to give me 3x, and just left the 12 and put that in the middle. But over here, if you do 4 times 4, you get 16. This is a negative, so it's like a negative 1 in front here. Negative 1 times the x is going to give me a negative x. Negative 1 times the 4 is going to give me a negative 4. So 16 plus the negative 4 does give me the 12. And 4x plus the negative x, this is going to combine to give me a 3x. So although this looks completely different, it is the same as a 12x plus 3. Just got to break it up and then make sure it does simplify back down to the same thing you had before. That's the key to creating an equation that has infinitely many solutions. If we're looking to create an equation with no solutions, the result always ends in two unequal numbers, so let's start with two unequal numbers. 12 doesn't equal 3. I put it in as equals because I do want to create the equation that has the equals between them, but I know that they're not actually equal. From there, I remember that I need to have the variables still need to cancel out. So I'm still going to have the variables with the same coefficient of 4 on both sides of the equal sign, so that if I subtract the 4x from this side, I'm going to have to subtract it from this side, and they're going to cancel out. But again, leaving it like this is too simple. We got to break it up a little bit further. And here's some examples of what I did to break it up. Here, if you look, I will do the 3 times the x is going to give me 3x. 3 times the 4 is going to give me a 12. Add this x to the 3x, I'm going to get 4x plus 12. So it does simplify the same thing. Here, 2 times 2x is 4x. 2 times the negative 3 is a negative 6. Add the negative 6 and the 9 to combine the like terms. I am going to end up with 4x plus 3, which is going to bring me back to that same equation I had before. But now it looks different. You get a little more flexibility with the no solution here, because you can create the one side and create the other side with the 4x there, the 4x plus 12 and the 4x, and then not have to worry about what the constant works out to be, because as long as it's not 12, then you're okay. So you can fudge these around a lot and just try and find something different, something that'll make up 4x plus 12 on one side and 4x plus something, or even minus something on the other side. And that will give you different equations that will end up having no solution. To write an equation that has just one solution, all you have to do is make sure the variables have coefficients that do not equal each other. They still need to be on both sides of the equal sign, because you want to make it a little bit of a challenge there. But you could do something like 3x plus 12 plus 4x is equal to 12x minus 5. I know the 3x and 4x are definitely not going to match up with the 12x. It doesn't matter what the actual constant works out to be, as long as this x and this x don't become a combined total of the same as the 12x on this side. So I just got to create something with different coefficients on the x when you simplify it.